So today we are going to discuss the code forces around 1013 problem E, which is interesting ratio. Recently, Misha at the IT campus Nemark camp learned a new topic, the Euclidean algorithm. He was somewhat surprised when he realized that A multiplied with B is actually equals to LCM of AB multiplied with the GCD of AB. Okay, and where GCD is the greatest common divisor and LCM is least common multiple. Now, Misha thought that since the product of LCM and GCD exists, it must be interesting to consider the quotient f of A. The guy tried to calculate this number now, not the product, but the division. LCM divided by, for example, he took A as 2 and B as 4. If he computed 2 comma 4, then LCM of 2 and 4 is 4, and GCD of 2 and 4 is 2, and the ratio is 2, and this is a prime number, right? And he obtained a prime number. Now consider FAB to be an interesting ratio if B is bigger than A and FAB is a prime number. So this is your definition of interesting ratio. Since Misha has just started studying the number theory, he needs your help to calculate how many different pairs of number A and B are there such that FAB is an interesting ratio and A and B is between 1 to n. So basically, you're given a range 1 to n and you have to compute how many such pairs of A and B exists such that FAB is prime. Okay, and here B has to be bigger than A. Every test case consists of a single integer n, okay, which basically tells you the range between which you have to find the pairs. For each test case, output the number of interesting ratio. So we have to count the number of interesting ratio. Let's see how are we gonna approach this problem. So what are we supposed to calculate? We are supposed to calculate FAB. Okay. And what is its definition? It is LCM of AB divided by the GCD of AB. And B is bigger than A. And from the Euclidean algorithm, we know that multiplication of any two number is the same as LCM of those two numbers multiplied with the GCD of those two numbers. So what is our input? Our input is a number n, okay, which tells us we have to find the pairs in the range 1 to n. Okay, we have to find those pairs of AB in the range 1 to n. So a brute force approach that we can apply to this problem is we can loop. We say that A can go from 1 to n, and then our B can go from A plus 1 to n. At every step, we calculate this ratio, and then we say that if this thing is prime, we increment the count. And finally, after getting out of the loop, we can output count. So this is the brute force method that we can apply. But natural, this brute force will give us time limit exceed. Why? Because it's a O of n squared solution. You're using a loop that run n times. And this loop also that is inside of it has a time complexity of n. So it becomes O of n squared solution. And it's been given that the value of n is 10 raised to the power of 7. So there is no chance for this to pass. Okay, so we will end up getting TLE. So now, how do we optimize this? To optimize this, we have to use some number theory. We just need the Euclidean algorithm to actually solve this problem. Okay, so this is my Euclidean algorithm that has been given in the question as well. Okay, but how do we use to solve the problem? The problem says we have to find the number of pairs such that f of AB is prime, isn't it? And what is f of AB? F of AB is actually LCM of AB divided by the GCD of AB. So these are the two equations that we actually have. Now, if we rearrange the first equation, we can write that LCM of AB is actually equals to A times B divided by GCD of AB. And now we can use this value of LCM in our second equation. If we do that, we get f of AB is equals to, now instead of LCM, I'm gonna use this value divided by the GCD of AB. Okay, so this means that FAB is actually equals to A multiplied with B divided by the GCD of AB squared, isn't it? Now, since we are writing GCD over and over again, let's represent GCD with G. So what we can say is that FAB is actually equals to this thing over G squared, right? Now remember, G is actually the GCD of A and B, right? Which means that G divides A as well as B, isn't it? G can completely divide A and G can completely divide B without leaving any remainder because it's a divisor of both A and B, the greatest common divisor. So if G can divide A, we can write that A is actually equals to G multiplied with some number. And similarly, since it also divides B, we can write B as equals to G multiplied with some number. Now, if we see this equation of ours, let's make it a copy. Now, instead of A, I will write G multiplied with X, and instead of B, I'll write G multiplied with Y. So instead of A, I'm going to write this, and instead of B, I'm going to write this. So this is my A and this is my B. So what does it become? It becomes G squared multiplied with X multiplied with Y divided by G squared. Well, the G squared gets cancelled, right? So our equation simplifies to FAB is actually equals to X multiplied with Y. And X and Y are some numbers, right? X and Y are some numbers. What can we derive from here? Now, remember, the question said that we have to find the number of FAB which are prime. Okay? Now, FAB is actually equals to X multiplied with Y. Now, it can only be prime if X multiplied with Y is a prime number, right? And X multiplied with Y can be a prime number only if X is actually equal to 1 and Y is equals to some prime number, or X is equals to some prime number and Y is equals to 1. These are the only cases when FAB is also prime. And remember, we have been given that B was actually bigger than A, right? So that means that G multiplied with Y was bigger than G multiplied with X, which means that Y was bigger than X. So if Y is bigger than X, then this second case that we thought of is wrong, right? Because we can't say Y is 1 and X is some other prime number, because even if you take the lowest prime number, it is 2. X cannot be bigger than Y based on this condition. Okay, based on this condition. So this automatically cancels off. So we just have to find such pairs that X is 1 and Y is actually prime. Remember, we have to find pairs of AB, right? So what was A actually equals to? A was actually equal to G multiplied with X and B was equals to G multiplied with Y, right? So this means that A will be equals to G multiplied with 1. Remember, we can only put X as 1. And B will be equals to G multiplied with Y, and Y will be some prime number. So G multiplied with some prime number. From the first equation, I can say that A is actually equals to G. And from our second equation, I can say that B will be equals to, since A is equals to G, and so G will be equals to A, I can write that B is equals to A multiplied with some prime number. This is the relation that we get between A and B. Very crucial relation. If FAB is prime, then that means this condition must hold. Now, moving further ahead, how do we make use of this information? How do we make use of this information to solve this problem, to actually find the number of pairs? Well, it becomes quite simple if you think now. You can pause the video and try to write down the code. So B is actually equals to A multiplied with some prime number. So let's say we loop, okay? We loop. Now remember, I have to find the pairs in the range 1 to n, and n was our input. So I'll take a loop. I'll take a loop from 1 till n. And let's say every time we assign our value a as equals to I. And what is our b going to be? Well, our b is going to be a multiplied with some prime number. But then the question is, where is this prime number? Where is this prime number? I'll come to it. The thing is, if we have A, we have to find the number of pairs, right? So the question is, how many different values of B that you can find for this particular value of A? This value that of B, the B should always be in the range, it should be less than n, which means that A multiplied with the prime number that you're going to multiply it with should be less than n, which means that the prime number that we're trying to find, it should be less than or equal to n over A. So now the question is, how many prime numbers are there which are less than this? If we are able to find that out, we get the number of B's that we can associate with A such that FAB is prime. We don't have to find B actually. We have to find the number of prime numbers less than or equal to n over A. And if we store this value in a variable, let's say x, what we have to do is every time we have to do result is equals to result plus x. That's it. That's all we need to do. Now the question is, how do you find this effectively? Well, you can make a loop. You can create a different function. Go till every number from 1 to n by a and check whether one number is prime or not. Or we can pre-store the value of all the prime numbers. Since we have to avoid the time limit exceeded, what we will do, we will pre-store all the prime numbers in a vector. So our vector of prime numbers is going to look something like this. So 2, 3, 5, 7, 11, 13, and so on. Okay, and so on. All the prime numbers in the range from 1 to 10 raised to the power of 7. All we have to do is search how many of them are actually less than or equal to n over a. How many of them are less than or equal to n over a? For example, if n over a is, let's say, if the value of n over a comes out to be 8, the question is how many prime numbers are there which is less than or equal to 8? You will say, okay, 1, 2, 3, 4, right? There are 4 prime numbers which are less than or equal to 8. So you can do a linear search over here. Again, linear search won't be very optimal. Now, since linear search will be very time consuming because the array can be very big because we are storing all the prime numbers from 1 to 10 raised to the power of 7, we can apply binary search. And in binary search, we can directly use the STL function of upper bound. So what is the upper bound of 8 in this array? If we see, the upper bound of 8 is going to be this value. And what is its index? Its index is going to be 0, 1, 2, 3, 4. 4 index. This 4 is actually the number of prime numbers that are less than or equal to 8. If you count 1, 2, 3, 4. That's it. So we can do it by simply finding the upper bound and then the index. We just have to find the index of the upper bound. Now, one question that might come to mind is, how do we store these prime numbers? How do we store these prime numbers? We need something called the sieve of Eratosthenes. We can use the sieve of Eratosthenes, which help us mark all the prime numbers, whether a number is particularly prime or not. Okay, and the time complexity of this algorithm is actually O of n of log of n. And after we have marked all the prime numbers using this algorithm, we can store that in a vector. So this is the code implementation of this algorithm. Okay, so you can look this up. It's a very important algorithm to find prime numbers efficiently. And then we create this vector is prime. So this is the vector that gets populated using the sieve of Eratosthenes. And then we create a new vector called the prime numbers. Okay, and here we store all our prime number from 2 to 10 raised to the power of 7. I started the loop from 2 because 1 is definitely not a prime number. Okay, so if it is a prime, we just push back in our prime numbers. And since we are going linearly, if you see, that means that prime numbers vector or array is going to be a sorted one. Okay, this is going to be sorted. And if it's a sorted, this means that I can use binary search over here. Okay, so that's the reason I can use binary search. And remember, we actually have to find the upper bound of n over a. So now let's see the actual implementation. This is the actual implementation of my solve function. Now, in every test case, we are taking an input n, and this is my answer. Okay, and I start from 1, I go up until n. I assign the value of a to I, and then remember the prime number that we are trying to find is gonna be less than or equal to n over a, right? So we have to actually find out the upper bound of n over a. So we store this n over a in a variable called prime, and then we find its upper bound. Okay, now this is the C++ STL that you can use. Okay, you can also write your own binary search, that is also fine, but I have done it using the STL. Now we find out the index. Now to find out the index, we just use this it minus primes dot begin. Now the index of the upper bound is actually the count of prime numbers that are less than or equal to n over a, and we just add it up to our result, and finally we just output our result, and that's how we get our answer. So hope it helps.